Just to emphasize my answer to a question Samar had earlier. Samar asked if you turn in homework late, will points be docked? No, they will not be docked. In case you haven't caught on, I'm always pretty lax about deadlines, being being sort of basically unable to meet them myself. At least I'm not hypocritical about that. And certainly when the world is on fire, I'm not gonna like sit here and like push deadlines on people like severely. So yeah, if you can take time over, if you have extra time over break and you can take time and catch up on your homework, that'd be fantastic. But please, for God's sake, don't go anywhere. Okay. Ooh, the world is so strange now. Okay, so let's do some math. Okay, yeah, that's right. So let me do a take two on this. I think the last 10 to 15 minutes of last time were pretty chaotic, and so let me actually just sort of start over. So I want to talk about computation, and so let F be a field, and so F bracket X is the ring of polynomials in that field. So F bracket X is all the polynomials with that you can think of with coefficients in the field F, and I want to take that ring F bracket X and kill the polynomial M of X. Set it equal to 0. And remember, this object over here. Let me remind you, is the ideal of all multiples of all polynomial multiples of the fixed polynomial M of X. And the idea is that killing the ideal M of X, it is really equivalent to setting M of X equals 0. Well, anyway, killing M of X means setting M of X equal to 0. That's what that's about, really. There we go. Okay, so we're looking at the ring that you get when you take all polynomials with coefficients in capital F and you set M of X equal to 0. So when you do that, let's call that new ring R bar. R bar. I sound like a pirate. R bar. How do we represent the elements of R bar uniquely? How do we compute the ring operations of addition and multiplication in the new ring R bar? And how can we tell if a particular element of R bar is a unit? And if it is, how do we compute its multiplicative inverse? So, this is sort of redoing arithmetic in the quotient ring R bar. Here's how we learn to write the numbers. And we are really very much doing redoing arithmetic. This second question is really asking, like, how do we do addition, subtraction, and multiplication? And over here, how do we do division? That was weird. How do we do division? There we go. Yeah. So the point is to redo arithmetic. Learn how to do arithmetic in the quotient ring R bar. And this is actually as we'll see, doing arithmetic in this new ring R bar, that's what it takes to compute in finite fields, which is one of the most useful things that we will discuss in this entire course. So believe it or not, this may be seem a little strange based on what we're about to do, but believe it or not, this is actually extremely practical. Questions?
Yeah. So fx is a field which consists of all polynomials.
Right. So remember. Let me remind you. So f. Yeah. So this is a subtle point that is confusing for everybody. So f is a field. I really there's really actually only one example that we'll deal with. So if you just think F is F2, the field of order 2, Z mod 2. If you secretly keep thinking about F as just being Z mod 2, that's great. So that's F. So, oh, by the way, who's asking the question?
Janvi.
Hi, Janvi. Okay, so Janvi, that makes sense?
Yeah.
So F is a field. F bracket X is not a field, is the ring, right? Because of all polynomials with coefficients coefficients in capital F. Right, and remember that f of x, f bracket x, sorry, is just a ring, not itself a field, because you can't, because 1 over a polynomial, because you 1 over a polynomial, because 1 over a polynomial is not a polynomial. So does that answer your question?
So f equals z mod 2 is an example, right?
Yeah, it's one example.
Okay.
And it's really essentially the only example that we'll deal with in this course for,
Okay.
for this particular construction of R bar.
Okay, yeah, that makes sense.
Yeah, and F, yeah, the example. I mean, it's kind of strange to think about. So, F equals Z mod 2 is literally the simplest possible field, and it's also it's literally the simplest possible ring, interesting ring they can think of. But oddly enough, the simplest possible example is the one that makes all the money, as we shall see. So, are there any other questions about this basic setup? Like, what is? Let me pull out for a sec. Pull back here. So, are there any questions about like what is f bracket x and what is R bar? Anything else? Anything else about the basic setup that we're trying to understand? Okay. So let me go back to the detailed look. All right. So now, here, so let's look at one particular example. So we're going to take polynomials with coefficients in F2, coefficients in Z mod 2, and we're going to look at the fixed polynomial M. And oh yeah, I should say why I like to use the letter M here. We think, or you want to think of M of x as the modulus. That's why we use the letter M for the polynomial that we're killing. It's because M stands for modulus, and that's very much like, that's exactly like the M in Z mod M. Yeah, so M of x is our modulus. Anyway, so but in terms of like fussy definitions being formal, so you take all polynomials with coefficients in F2 bracket x. We look at a single polynomial, M of x is x to the fourth plus x plus 1. We let I be the ideal of all multiples of M, so just M times any polynomial. And we let F2 bracket alpha, so we're going to use the notation F2 bracket alpha to represent the quotient ring. So this is our R bar. So this is our R bar over here. Is F2 bracket x mod I, and we sort of we will usually use the notation F2 bracket alpha to represent this kind of a quotient ring, and alpha will be our standard abbreviation for the coset x plus I. I don't keep writing one of these x plus I, keep writing these x plus i's, because in any case, in practice, you can always think of elements of F2 bracket alpha of elements of R bar of this quotient ring as polynomials in alpha, and they're subject to the rule that alpha to the fourth plus alpha plus 1 is equal to 0, precisely because alpha is is an abbreviation for x plus I, and we know that x to the fourth plus x plus 1 is equal to 0. So in fact, we only need polynomials of degree less than or equal to 3. I guess I should finish that sentence. We only need polynomials of degree less than or equal to 3 to represent all elements of R bar equals of our quotient ring. R bar equals F2 bracket alpha. Okay, so here's an example. All right, and so now, can somebody type in the chat a sort of not too large polynomial of, but degree, a polynomial degree bigger than 3, like 4, 5, or 6, or 7. So, let me try something easier. Can somebody can everybody type in a random number between 1 and 7? 5, 6, 7, 3. Okay, so let's look at alpha. Oops. Let's look at alpha to the 7th plus alpha to the 6th plus alpha to the 5 plus alpha cubed. All right. So right. So I claim. So I want to. What I want to do is I want to simplify this element of. Oops. I want to simplify this element of f2 bracket alpha. I want to take this element and sort of write it as a polynomial of degree less. Oh, I hate that. Of degree. There's just no way to do that, huh? Oh well. So I want to rewrite that element as an element of degree less than or equal to 3, and it's 3. And I want to observe here that this is 3 because why did I pick degree 3? Why is it that I can write things write and be able to write this as degree less than or equal to 3 if I can actually move the chat window someplace where I can actually write over here. 3 is, there we go, 4 minus 1. So it's so if and the 4 is the degree of the thing we're killing. All right. Anyway, so the point is, if we have, oops, let's see if that works. Yeah, if we have, because alpha to the 4th plus alpha plus 1 equals 0, right? So in general, if you take a ring of polynomials and you kill a single polynomial, what you want to just think is that you have polynomials in some new variable, say alpha, and you're setting the killed polynomial equal to 0. So that means, so if I know that alpha to the 4th plus alpha plus 1 equals 0, that means that alpha to the 4th is equal to minus alpha minus 1, which is in turn equal to, but since all our coefficients are mod 2, so remember this f2 over here means that all our coefficients are mod 2, we see that alpha to the 4th is equal to alpha plus 1. Yeah, so why, again, why is that? Why do we get that? Why do those minuses become pluses? That's because all coefficients are taken mod 2. All right, so how are we doing so far? So does everybody see why it is that alpha to the 4th is equal to alpha plus 1? Or are there any questions? So if you could, if a lot of you could say either type yes, I understand why alpha to the 4th is equal to alpha plus 1, or ask a question in the chat, that'd be great. So go ahead. Okay, great. But all right, so if we have an alpha to the 4th, we can replace it with an alpha plus 1. Fantastic. We don't have an alpha to the 4th over here. What we have is an alpha to the 5, 6, and 7. Well, that's okay. Whoops. I want to be over here, actually. I want to do a pen. Because alpha to the 4th is equal to alpha plus 1, that implies that alpha to the 5th is equal to alpha squared plus alpha. And just in case this isn't clear, how did I get this new rule? Oops, that didn't work. How did I get this new rule? I got this new rule by multiplying both sides by alpha. So yeah, so if alpha to the 4th is equal to alpha plus 1, it must follow that alpha to the 5th is equal to alpha squared plus alpha by multiplying both sides of that equation by alpha. and alpha to the 6th is equal to alpha cubed plus alpha squared. Ooh, and here's a tricky one. Alpha to the 7th is equal to alpha to the 4th plus alpha cubed. But again, alpha to the 4th is equal to alpha plus 1. So this is actually equal to alpha cubed plus alpha plus 1. So so does that make sense where I got these new rules? So yeah, does that make sense where I got these new rules that alpha to the 4th is alpha plus 1, and alpha to the 5th is equal to alpha squared plus alpha, and alpha to the 6th is this, and alpha to the 7th is that. So I can replace all these terms, alpha to the 5th, alpha to the 6th, and alpha to the 7th, with polynomials of degree at most 3 in alpha. So does that make sense to everybody? Again, please type yes in the chat window, or ask a question if you can articulate something. You can just type Y. Y is good. Oh yeah, how did I get? Okay, so Sammer asks, how did I get alpha cubed equals alpha plus 1? Alpha cubed plus alpha plus 1 at the end. Well, where I got that is that alpha to the 4th. So as soon as I get to that alpha to the 4th term, I can now I don't like that. But I can apply the alpha to the 4th rule again. Yeah, I replaced it with alpha plus 1. That's exactly right. Where did the negative sign go? So the negative sign that yeah, let me yeah, where did all the negative signs go? So remember, we're taking all coefficients mod 2. So this is going to be sort of true. So minus equals plus. Oops, I didn't quite make that. Let me move that out a little bit. So because we're working with coefficients mod 2, plus 1 is equal to minus 1. So this is a thing I really like about working with coefficients mod 2 is that you can never make any sign errors because there are no signs, because plus is equal to minus. A remarkable fun fact. Yeah. So why did the minus alpha minus 1 change into a plus alpha plus 1? Well, minus is equal to plus because 2 is equal to 0. So good question, Johnny. Does that make sense? Yeah, it's great. It's a paradise. Plus is minus. Like the number of errors is so greatly reduced. Anyway, so what we get now is we get alpha to the 7th, just to finish simplification. That's equal to alpha cubed plus alpha plus 1. And alpha to the 6th is equal to alpha cubed plus alpha squared. And alpha to the 5th is alpha squared plus alpha. And alpha cubed is still alpha cubed. Oops, if I can actually write that. You know, they say that you shouldn't write with a mouse, but actually writing with a mouse is pretty good for writing little tiny details. Anyway, so the point is, so when I add up all these terms, and remember, actually, let me remind you where each of these terms came from. This term came from alpha to the 7th. This is what happened to alpha to the 6th, and this is what happened to alpha to the 5th. So this initial element of R bar, alpha to the 7th plus alpha to the 6th plus alpha to the 5 plus alpha cubed is equal to all this stuff. Anyway, so the point is, when we add all this stuff together, well, we have 1, 2, 3 alpha cubes, but since 2 is equal to 0, 3 alpha cubes is really 1 alpha cubed. Okay, yeah, Than, I see your question. I'll come back to that in a second. So similarly, we have this alpha squared plus alpha squared. We get 2 alpha squared, which is 0. So I'll leave that out. Actually, let me write that in a different color. I'll use this in a very pale ghostly green. Plus 0 alpha squared. And similarly, we have alpha plus alpha. That's 0 alpha. And then finally, well, the 1 is just a 1, and it just stays there. And so we get plus. So the simplification of alpha to the 7th, the full simplification of alpha to the 7th plus alpha to the 6th plus alpha to the 5 plus alpha cubed is that in this quotient ring, we are that all that stuff is equal to alpha cubed plus 1. And in a very similar way, any element of this quotient ring, F2 bracket alpha, can be represented uniquely as a polynomial in alpha of degree less than or equal to 3. I think this example shows that you can get everything equal to polynomial of degree less than or equal to 3. You do the same kind of thing, even if you have to go up to alpha to the 20 and reduce a bunch of times. But the point, the unique part actually comes from the uniqueness part of the division theorem. But okay, all you need to know is that but you don't need to know that. You need to know that. You just need to know that this representation is in fact unique. Okay, so let me return to Than's question. So Than asked, why are we always dealing with mod 2? So the reason that we are dealing with mod 2 is that here's why. We start out with polynomials with coefficients mod 2 and then kill. So the coefficients are still mod 2. It's not like you sort of get rid of, it's not like you can get rid of that mod 2-ness by killing something that, if 2 equals 0 and you kill something, you still have, 2 is still equal to 0. So sorry, I have an occasional tendency to excessive violence in my metaphors. I apologize for that. But anyway, yeah. So right, if your coefficients start out mod 2, and you mod and then you mod out by some more stuff, 2 is still going to be equal to 0. I mean, you start off in a ring where 2 equals 0, and if you add more rules, that will never undo the rule that 2 equals 0. So no matter what, you're always going to end up with 2 equals 0. So does that make some sense, Than? Yeah. So here's a picture of the entire. Yeah, you're welcome, Than. That's an excellent question. Thank you. Yeah, here's a picture of the entire procedure. You start off with a ring that has coefficients mod 2, and then you sort of mod out by something. So coefficients are still mod 2, and the point is that if the thing you mod out by has degree 4, then you can use rules like this to reduce everything, every polynomial to a polynomial of degree at most 3. Oh yeah, so Ryusei asks, how was the rule alpha to the 4th plus alpha plus 1 equals 0 chosen? The rule alpha to the 4th plus alpha plus 1 comes from the fact that we're modding out by x to the 4th plus x plus 1. If you're asking where does the x to the 4th plus x plus 1 come from, well, that was the initial setup of the problem. So that's if you think of this as a problem, how do I compute in this ring? That's a piece of given information that x to the 4th plus x plus 1. All right, thanks, Ryusei. Any other questions? Okay, so let me go back to the big view, and so let me talk about computing in this ring. And actually, I think we sort of, I think we sort of saw, we actually kind of saw what addition looks like. So let me just skip. I'm going to skip the. So I just want to do a multiplication example. I think that will suffice. So let me sort of scribble this out, and let's just make this beta times gamma. Okay, so can somebody? Let's see. So somebody quick pick some set of numbers, subset of 3210. Somebody type it in the chat window. Some subset of 3210. 01. So that's like I'll do alpha cube. So some folks, somebody picked 0, 1, and somebody else picked 3. So I'll have alpha cube plus alpha plus 1. And can somebody else pick another subset of 3, 2, 1, 0? I'll do 3, 2, 1, 0 itself. Okay, alpha squared plus alpha cube plus alpha squared plus alpha plus 1. All right. So now, you know what? I'm gonna chicken out, and I'm going to erase the last two terms because just to save a little time. So zap this, zap, 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 zap. Okay, so all right, so just make this a little shorter. All right, so now what I want to do is I want to multiply beta times gamma in the ring F2 bracket alpha under that same rule, alpha to the fourth equals alpha plus 1. Right? This is the same F2 bracket alpha from before, so we have that same rule: alpha to the fourth equals alpha plus 1, and alpha to which means that alpha to the fifth equals alpha squared plus alpha, which means that alpha to the sixth is equal to alpha cubed plus alpha squared. So this is the same. We're staying in the same ring, and so the same rules will apply. Oops. Okay, so that's what we're doing. That's the ring in which we're working. All right, so now when I multiply beta times gamma, I'm going to get 6 terms. I'm going to get alpha to the, I'm going to get alpha to the 6th plus alpha to the 4th plus alpha cubed. Oops. That I get from alpha cubed times alpha cubed plus alpha plus 1, and then I add in the other part of the FOIL, alpha squared times alpha cubed plus alpha plus 1. So I get alpha to the 5th plus alpha cubed plus alpha squared. Right. Yeah, let me do that. I'll do it this way, just to sort of show you where those terms came from. So is everybody good with that so far? Seven. Okay. Kyle, was that a correction, or did you just randomly type in a 7? You randomly typed in a 7. Okay. Okay. So, all right, the 7's right over the y. Okay. So remember, 2 is equal to 0. So those two terms, the alpha cubed and the alpha cubed over here, the first alpha cubed and the second alpha cubed cancel out, and so we now get, but everything else survives. So we get alpha to the 6th. Oops. We get alpha to the 6th plus alpha to the 5th plus alpha to the 4th plus no alpha cubes because the alpha cubes cancel out plus alpha squared. And so let's see, and then we apply our rules. So alpha to the 6 is alpha cubed. Alpha to the 6 is alpha cubed plus alpha squared, and alpha to the 5th is equal to alpha squared plus alpha, and alpha to the 4th is equal to alpha plus 1, and alpha squared is just alpha squared. And so we get a bunch of cancellation here again. I mean, so these two. Yeah. So Fan is asking. I think you might be repeating this, but why do we have to do alpha to the 4th plus alpha to the 5th plus alpha to the 6th on the side? It's exactly right. I'm just repeating this because so I can remember how to reduce. So what is really going on here is that these are the same reduction rules as before. Yeah, so I'm just, so I repeated that thing on the side just so I could look up and remember what the rules are for computing in this ring. You know, the quotient, the modulus of the ring, of your ring defines what your reduction rules are, but it's sort of convenient to have them right there. So I'm just repeating them so I can remember what to do. That's all. Fan, does that make sense? Yeah, I'm just repeating them for convenience because I look up and I see, because I can look up and I see that, oh, x to the sixth, sorry, alpha to the sixth tells me that alpha to the sixth is equal to alpha cubed plus alpha squared, and alpha to the fifth is equal to alpha squared plus alpha, and alpha to the fourth is equal to alpha plus one. And I just read them right off the rules up here. Samar asks, are alpha to the fourth, alpha to the fifth, and alpha to the sixth always the same, or is it just for this example? It's just for this example. And let me say exactly where it is that those rules are chosen. It's the same reduction of rules as before, comma, based on the initial data that m of x equals x to the fourth. Our modulus is equal to x to the fourth plus x plus 1. So, and later, I think later on, we'll do an example. Actually, momentarily, we'll do an example with a different modulus, and then you'll have different reduction rules. So, Samar, does that answer your question? Okay. All right. Anyway, so yeah. So returning to, so let me finish up simplification here. So the two alpha squareds cancel out. Whoa, that was weird. Oh, I want to do this instead. So those two alpha squareds cancel out, and this alpha plus alpha also cancels out, and but everything else is sort of left over, and so what we get is our final simplified answer is alpha cubed plus alpha squared plus 1. There. Oh yeah, Johnny, thank you for asking that question, and Fan, thank you for answering it. So Johnny asked, how do the alpha cubes cancel each other out? Does it have something to do with plus equals minus? And Fan said it's because we got 2 alpha cubed and we're in mod 2, so it cancels out since 2 is equal to 0 mod 2. And that's exactly right. Thank you very much. Great. Good. So it seems that, well, I don't want to presume anything, but I think this definitely stinks less than last time. How about that? It's less confusing. This is less confusing than last time. Okay, so is everybody with me so far on this? Okay. So, oh yeah, okay. I'm going to do so. So in general, so we've worked. So in this, actually, let me go back to the whole page display for just for a bit. So in this particular example, we have worked out how to represent elements. So any element can be represented by a polynomial of degree strictly less than the degree of the modulus. And using these rules determined by the modulus, we can add two of these polynomials and multiply two of these polynomials. So we've worked out addition, subtraction. Well, subtraction here is the same as addition, but subtraction would be similar. And if you start off with a different base of coefficients, and multiplication, and so now we have a ring. So so let me sort of state what happens in general. So in general, and here's our standard notation. So and let me emphasize this word again. Remember, m of x. Oops, I want to be this one. I want this to be in blue, and I want to say that m of x is our modulus, is the modulus of our quotient ring. f bracket x mod m of x. So here's so what we saw in that one particular example also works in general. So so for our notation, m of x is the modulus, and let I be the principal ideal generated by m of x. That's the set of all things, all multiples of m of x, and that's what we end up killing. So in this quotient ring f bracket x mod m of x, every coset has exactly one representative of degree strictly less than the degree of the modulus. So that's sort of the general statement of what happens up here. Just as up here, our modulus had degree 4, we were able to reduce everything to degree at less than or equal to 3. This is saying that if whatever your degree is, you can reduce everything to a polynomial of degree strictly less than the degree of the modulus. And so we call that coset representative. Oh, and there's like a typo here. That's right. So this is just I. And 2b. So we define the reduced representative of an element of the reduced representative to be the unique representative coming that has degree strictly less than the degree of the modulus. And so here, this final answer here that we get up here and the final answer that we get over here, those are both reduced representatives. And so so we abbreviate that coset x as we did in our example, x plus I as alpha, and in general the coset f of x plus I is written as f of alpha. So the terminology that we have to describe this, it comes from the following ideas. So since we're setting the modulus equal to 0, modulus m equal to 0, m of alpha by definition essentially is equal to 0, and so we will sometimes call alpha a root of m of x. So the terminology for that is sort of the general thing that happens to be true is that just as we can represent the elements of Z mod m as the integers 0 to m minus 1, we can represent the elements of R bar, which is f bracket x mod the polynomial m of x, as polynomials in alpha, in the letter alpha, of degree up to d minus 1, where d is the degree of m of x. Oops. Where d is the degree of, open parentheses, m of x. And so in fact, the terminology, instead of having to say f bracket x mod m of x many times, we sometimes describe that ring. Actually, we will often describe that ring as f bracket alpha, f adjoin alpha. Oh yeah, so I should say how this mysterious term, this f bracket alpha, is pronounced. So that is often pronounced. Oops. So that f bracket alpha is going to more usually pronounced f. That's quote f adjoin alpha. Pronounced f adjoin alpha. So we will call that ring f adjoin alpha, where alpha is a root of m of x. In other words, i.e., to say that alpha is a root of m of x means that m of x is the modulus of the ring f adjoin alpha. So yeah, oh, sorry, that's my phone. This is one of the exciting things about teaching at home, huh? I think that was the school district reminding us that we have to stay home. All right. Okay. So anyway, so to say that alpha is a root of m of x means that m of x is the modulus of the ring f adjoin alpha. So this is that's the terminology that we will use, and you'll sort of see how this is used in practice later on in a bit. Okay. So this is just sort of saying that the thing, all this is just saying is that the thing that we did in our example works in general. So for addition and multiplication, so if R bar is f adjoint alpha, where alpha is a root of m of x, see, that kind of flows trippingly off the tongue, right? When R bar is f adjoint alpha, where alpha is a root of m of x. Let me actually write out what I'll write up here what I actually said. I said, quote, R bar is f adjoint alpha, where alpha is a root of m of x. That's how I pronounce that. So let R bar be f adjoint alpha, where alpha is a root of m of x, and let d be the degree of your modulus m of x. So since any element of f of alpha can be expressed uniquely as a polynomial in alpha of degree at most d minus 1, which we just saw and the sum of two such polynomials is a polynomial of degree at most d minus 1. Addition in f of alpha, at f adjoint alpha, is just ordinary polynomial addition with coefficients in f. So actually, if you look at what happened back in the examples, once you have things to the point where you're adding polynomials, you don't get any higher degree polynomials, and so you don't have to use those reduction rules anymore. You just add polynomials and use the fact that in that case 2 is equal to 0. On the other hand, when you take products for f of alpha and g of alpha in f adjoint alpha, to find the product f of alpha g of alpha, we compute f times g as a polynomial and then reduce using long division by the modulus m of alpha, with the remainder being the reduced representative, or better, use our reduction rules. Use the reduction rules coming from the modulus m of alpha, m of x, or m of alpha, either way. I think m of x is probably a better way to put it if you're going to be fussy. All right, so yeah, so all this is just saying that the thing that we did here in this particular example. So all that is just saying formally that the procedure that we use in this particular example works in general. Yeah, this is really one of these topics where the example is clearer than the general case, communicates the general case perhaps better than actually writing out the general case. But yeah, this is just saying that what we did will work all the time. Okay, so so we did addition and also subtraction and multiplication. So are there any questions about addition, subtraction, multiplication before we get to division? Division is a little harder. Is everybody ready to move on to division? Say yes or ask a question. Okay, great. So why is I forget this is the corollary of? Anyway, this is essentially a corollary of the stuff we did about the Euclidean algorithm before. But the point is, so if we're working in f adjoint alpha, where alpha is a root of m of x, if you have b of x, so if b of x, so let me be a little bit careful about b of x versus b of alpha. So if b of x is a polynomial with coefficients in capital F, then the corresponding element b of alpha in R bar, that has an inverse in R bar exactly when the GCD of b and m is equal to 1. In which case the inverse g of alpha of b of alpha can be computed by solving this equation. Oh no, that thing. So remember that horrible equation that you had to do all that work to solve, something times m of x plus something times b of x is equal to 1. Well, this is what this is. So actually, let me remind you how you compute inverses. So actually, let me backtrack a little. Let me remind you how to convert inverses mod m where m is an ordinary integer. So remember that A has an inverse mod m exactly when, if and only if, the GCD of A and m is equal to 1, is equal to 1. And remember, oops, and remember that we find the inverse x of A by solving ax plus my equals 1 in integers using Euclidean reduction. So remember we did that way back in the day? Oh, those are simpler times. So does everybody vaguely remember doing that back in the day? You know, you had to use Euclidean algorithm to find the GCD of A and M. That actually also tells you how to solve ax plus my equals 1. So the same thing works here. So this equation here, this equation number 1 here, is the equivalent of well, I guess I have a b here instead of an a, but yeah, this is the equivalent of ax plus my equals 1, except with polynomials. And so yeah, and so in order to actually find an inverse, that's what we're going to have to do. And so as a special case, just like Z mod M is a field exactly when M is prime, well, F adjoint alpha, this R bar over here, is a field if and only if its modulus is irreducible. So an irreducible modulus equals a field, gives a field quotient. Quotient is a field. Okay, so yeah, so again, I mean, it's more complicated, but it really, so the situation looks more complicated. It is more complicated, even calculationally, as we'll see. But the point is that that it's really, if you really understand, right? So this is one of these things this sort of thing I always like to say. If you really understand the integers, then then you'll understand polynomials. But you know, that's true. But I'm maybe being a little, maybe cheating a little. But when I say like what I mean by really understand means you sort of understand the axiomatic basis of the integers. So if you understand the integers on the level of ring theory, then you automatically understand polynomials, and, which, as you'll see, is a sort of money making thing. Anyway, so yeah, so everything works for polynomials exactly as it does for integers. I think I was going to ask for questions, but I think it's better for me to do an example, which I think is coming up on the next slide if I remember correctly. So let me do an example. Look, example. There we go. So now, I again, as I usually will in this case, our sort of initial field would be z mod 2. So our coefficient field will be z mod 2. And our modulus will be x cubed plus x plus 1, which is which we think of as a polynomial in x with coefficients mod 2. And f2 adjoint alpha will be f2 bracket x mod m of x. So our modulus is x cubed plus x equals x cubed plus x plus 1. And our sort of defining rule for everything is alpha cubed equals alpha plus 1. Okay, and so here's an ill-chosen idea. I'm going to have you guys pick a beta, I guess. So can somebody type in again? Can somebody type in some subset of 3210? 1, 2, 3. Okay, there we go. So let beta be alpha cubed plus alpha squared plus alpha. And I want to, and the goal is to find beta inverse, if possible. Well, I think you guys actually showed or saw in some homework assignment that alpha x cubed plus x plus 1 is irreducible over F2. And so there will definitely be some beta inverse. Okay, so right. So I want to solve, well, I want to find the GCD of, and so our B of x is going to be x cubed plus, move this over here, plus x, oops, undo, plus x squared plus x. And so in order to solve beta gamma equals 1, I want to find the inverse gamma equals beta inverse. I will now have to find use the Euclidean algorithm to find the GCD of B and M, which I actually know is going to be 1, but actually I need to know the details. All right, I need to know the details of the calculation. So let's see how this goes. I will probably need another page, but that's okay. So that's fine. What else do we have to do, huh? All right, so I'm going to divide. I guess I'll start off with m, which is x cubed plus x plus 1. And I'm going to divide that by x cubed plus x squared plus x. And that goes in once. And we get x cubed. X cubed plus x squared plus x. And then we get a remainder of x squared plus 1. Okay. All right. And so, well, okay, that's first step. And then the second step is we're going to divide. So then the old divisor becomes the new, the old divisor becomes the new thing you're dividing into. X cubed plus x squared plus x plus 0. And we're going to divide that by x squared plus 1. Well, that so x squared plus 1 goes in x times, and we get x cubed plus x. We're not done yet. We have an x squared here, and then we have a plus 1. So that so x squared plus 1 goes into x squared 1 time. We get x squared plus 1. Whew. And we get a remainder of 1, and so that must be the GCD. Oh my God! I think I actually. Can you believe I cannot believe that I actually did long division twice correctly on saved on YouTube. Look, YouTube, I can actually do long division under pressure, or something. Well, let's see if I can actually do multiplication. Okay, so anyway, the point is that so oh yeah, actually I should use a different color here. So let's see. So x cubed plus x plus 1, that was our m of x. And so and this over here was our b of x. And so we see that m of x is equal to, oops. And we see that m of x, orange is fine, is equal to 1 times b of x plus x squared plus 1. So that's what that long division tells us. And now b of x, we saw below, is equal to x plus 1 times x squared plus 1, x plus 1 times x squared plus 1 plus 1. Oh yeah, I will need a new page here. Edit page, insert page. There we go. Okay, so I'm going to rewrite the again rewrite these two. Oops. Ooh, right. So Than, let me interrupt this to answer Than's question, which has been sitting there for a while. So Than asks, in B, can the alpha power be larger than 3? Well, it can be. I mean, it can be, but there's no need for it to be. So Than asked, so I picked, oops. You know, I'm being silly because I should have actually started off with a power up to 2. My bad. That's fine. Well, actually, I shouldn't have actually started with the element alpha cubed, because let me actually show you that I actually did. Not only do you never need a power bigger than 3, you actually never need a power bigger than 2, because alpha cubed is actually equal to alpha plus 1. And that's alpha squared plus alpha. So I'm actually finding the inverse of alpha squared plus 1. So sorry, I should have done that in the first place. Okay, so yes, so I can do long division under pressure, but I seem to have forgotten the theory under pressure. Oh well. Anyways, and so actually it's not so surprising. Look, there's that x squared plus 1. So we just saw that b of alpha is equal to x squared plus 1 mod m of alpha. There we go. All right. Anyway, so let me just go ahead and finish the calculation, even though I kind of did it in an inefficient way. So we have that alpha squared plus 1 is equal to m of x minus b of x, which is the same thing as m of x. I'll write it out as m of x minus b of x, though it's actually the same as m of x plus b of x, because plus is equal to minus. Wacky. And so, we see from the second equation that that 1 is equal to b of x minus x plus 1 times x plus 1 times x squared plus 1. All right. And oops. Sorry, that alpha should be an x here. And so we see that this is 1 is equal to b of x, and remember minus is plus x plus 1 times x squared plus 1, which is m of x plus b of x, which is because plus is equal to minus. So whatever. And now remember mod m of x, and if you look back, you do the same sort of calculation. We get 1 is equal at this point, since we are now working mod m of x, we can replace the x with an alpha. So now right, so we can replace x with alpha, and so we get 1 is equal to b of alpha plus 1 times b of x, because mod m of x, we see that because we know that alpha is a root of the modulus, and so m of alpha is equal to 0 by construction. And so we have that 1 is equal to b of alpha times alpha plus 1, which is equal to 1 times b of alpha plus alpha plus 1 times b of alpha. So this is equal to alpha plus 2. So 1 is equal to alpha plus 2 times beta. Remember, beta, the whole point was that beta is equal to b of alpha. And so finally, we see that which is equal to alpha times beta. And so beta inverse equals alpha. Whew! Brooklyn, we did it. Fantastic. Okay. So I added an unnecessary step, but that still worked out. We were able to compute that the inverse of that beta is equal to alpha. I feel like I should check that, huh? Let's check that. So let's check that. So beta was actually alpha squared plus 1. And so beta times alpha times beta is equal to alpha cubed plus alpha. And what was our reduction rule? Our reduction rule was alpha cubed equals alpha plus 1. So we have alpha cubed equals alpha plus 1. That's the rule that we get from our modulus. And so this is equal to alpha plus 1 plus alpha. Oh, so satisfying. That was like resting a table on your foot. It hurts, but when you take it off, it feels great. or something like that. Yeah, you know, one thing about doing this online is it's like much more painfully obvious that I spend a lot of time laughing at my own jokes. Oh well. Anyway, yeah. So such are the effects of staying at home. All right. Any questions? Oh my goodness, that was quite some. That was quite a calculation. But so is everybody? Can everybody at least make their peace with that, or are there sort of immediate questions about how to find the inverse of an element? All right. I guess you know what? I will have to find the place in this when I post the video. I'll find the place in the video where this calculation starts, and I'll say you can skip to 45 minutes in, and then watch me do this calculation for 20 minutes. And it's sort of worth trying to do yourself. All right. For now, though, let me move on. Yeah, especially since we have 9 minutes left. Let me go ahead and move on to a little bit of theory. Whew. Which honestly would be much easier than the calculations. Okay, so I want to talk about I want to introduce this idea of principal ideal domains. So the property of being a principal ideal domain is a key property that explains much of what the integers and a ring of polynomials with coefficients in a field have in common as rings. The thing that sort of makes, I was just saying, the integers, if you get anything out of sort of theoretically out of this course, I want you to get this idea that the integers, the algebra of the integers and the algebra of polynomials with coefficients in a field are essentially the same. They're basically the same kind of ring, or at least they're always very closely analogous. And so this one particular definition tells you is a key property that tells you why exactly the way in which the integers and polynomials are the same kind of ring. So to say that a ring R is a principal ideal domain or PID means that R is an integral domain, that is, it has a zero factor property, and that every ideal of R is principal. Or in other words, the interesting condition, the second condition, which is the interesting condition, says that if I is an ideal of R, then I is equal to the parens A, the ideal generated by A, the set of all R multiples of a single element A for some I guess I should say fixed. If I can actually write here, some fixed element A and I. I guess I really mean some A and R. Not bad. Yeah. So these are the only ideals you see are the multiples of a single element. So, for example, oh yeah, because it's good. We'll have time to do this. All right. So it's important to see what. So I want to explain why it is that both the ring of integers and the ring of polynomials, coefficients in the field, are principal ideal domains. So that's the theorem. If R is equal to the integers, or if R is equal to the ring of polynomials with coefficients in some field F, then R is a PID. So suppose I is a non-zero ideal of Z. The zero ideal is not so the zero ideal is generated by 0, so we don't have to worry. So that takes care of that case. So let D be an element of that ideal capital I, which has the smallest possible non-zero absolute value. So again, so let D be an element of capital I that has the smallest possible non-zero absolute value. So suppose we have some other element A in I. So remember the signed division? No! Oh my God, we have to remember something for like week 3. Crazy. All right, as if there was some plan to this course, huh? So the sign division theorem says that A is equal to QD plus R. Well, all the division theorems always say that something like this. But the interesting thing is the uniqueness is always talking about what properties do we have in the remainder. for some q, for some integers q and r. And the important part is that the absolute value of r is strictly less than the absolute value of, or less than or equal to, sorry, the absolute value of d over 2. I mean, and the point is, the over 2 isn't that important. The important part is that the absolute value of r is strictly less than the absolute value of d. So I hope, does everybody remember this? Hope everybody remembers this. You know, if you're watching this on YouTube, this would be a good time to sort of pause the video and go back and look at this in the book, Sine Division Theorem. By the way, somebody's making scraping noises. I'm not sure who, so you might want to make sure your mic is off if you don't want to be recorded with your scraping noises to be recorded. I mean, it wasn't so bad. Okay, so the point is now that so r is equal to a plus, oh, sorry, minus. I know I like it when plus is equal to minus, but that's not always true. Is equal to a minus qd. But oops. But d is in I, and q is in the ring R, which means that dq is in I. Remember, and the key point there is that ideals are closed under multiplication by elements in the larger ring R, and not just inside not inside the ideal itself. And also, and A is in I, and now we see that QD is in I, which means that A minus QD equals R is in I. But, and here's the key point, but D is chosen has a smallest non-zero absolute value, and the absolute value of R we saw up here is actually smaller than the absolute value of D. So because D has the smallest possible non-zero absolute value from among all elements of capital I, it must, and the absolute value of R is smaller. Well, the only way that can happen is if R equals 0. And so I didn't quite finish this up in the page here, but that's okay. That works. Oh my gosh, that worked. I was hoping that worked. So let me say that again at somewhat greater length, because I was just trying to cram that into the end of the page here. So again, D has the smallest possible absolute value from among non-zero elements of our ideal I, and R is an element of I with a smaller absolute value than D, so R must be equal to 0. So A is equal to dq qd. In other words, any arbitrary element of I is a multiple of D, i.e. the ideal I is equal to the multiples, the set of all multiples of D, which is the ideal generated by D. Whew. So we're done. Yay. Woo. All right, and I really wanted to go through that at least let's see what's left. Okay, so yeah, I really want to sort of go over that because that's sort of on your next homework. Is actually sort of imitating that for where r is equal to polynomials and not the integers. But there's the full proof for the integers. Okay, and let's see what do we have left here. All right, so we have a few things to clean up, which I'll just, you have better things to do, I know, or at least other things to do. Maybe not better things to do. So we'll talk about very briefly about minimal polynomials and factorization after break, when we sort of pick this up where we leave off here. And so, you could have been anywhere in the world today, or at least you could have been anywhere virtually in the world. And so I thank you for spending your time here. Oh yeah, for exam 2, which chapters are going to be covered? I'm not quite sure, but I think probably. So John B. finally asked for exam 2, which chapters are we going to cover? It's going to cover roughly problem sets 4 through 7 or 8, and I think probably probably chapters 5 through 7. So let me just say probably chapters 5 to 7. I have to think about that a little bit, but yeah, I think chapters 5 through 7. How are we doing the exam? So we have not. This is a good way to spend some time before break. So I haven't quite decided yet, but probably what we will do is what will happen is I will email you or the exam or post the exam on Canvas at 10:30 at 10:30. Oh yeah, Fan asked Miss Monday's class, but I didn't know then either. So what will happen is, at 10:30, I'll post the exam or email it to you, and you guys can, or maybe I'll just put it on the screen. I'll just put all the questions on the screen. It's all of the above, and you can just read the problems, and then do them out write them out on your own paper, and then scan them in we'll take the last 10 minutes of class, and have everybody scan in their written answers on their own piece of paper. Does that sound like a reasonable system? I mean, we have to put in some sort of we would have to put in some kind of proctoring system over that, but does that make some kind of sense as a reasonable system? Right, let me ask. Yeah, so something like that. Will it be open book? Um, uh, Let me get back to you on that. Maybe. I mean, please don't talk to your friends. Yeah, so there's always. I was thinking about this. There are always people in a crisis who will seize the opportunity to do something unethical, like loot the TV store, or I don't know, try to steal $500 billion from the federal government by passing some sort of hinky law. But yeah, I mean, so we might. Yeah, so it certainly. Yeah, I think we might. I'm somewhat leaning towards something open bookish. I don't know if that'll help so much, uh, uh, but yeah. So I mean, but certainly, I think it's probably not the right situation in which there's going to be some question where you just recite something. That's probably not a suitable question for this situation. All right, so let me think about it. But huh, let me ask the fatal question. Well, I don't know. Yeah, uh, we'll, well, okay, let me think about it. Okay. Yeah. So if we only, oh yeah. So and Jennifer asked if we only have one more midterm, how will the grade weight change? I will give you new percentages when you get back. Uh, yeah. So how will the questions that you have to ask me during the exam be resolved? Yeah, that is another thing I have to really think about. Um, yeah, that kind of depends on the proctoring system. So if you have you've had some experience with these online proctoring systems, has anybody taken an actual proctored exam since this all started? Yeah, so a lot of no's. Who knows? Um, yeah, so some people have been doing take home. Somebody took a quiz on a campus. Go
Right
ahead.
next to it, it says G4 Online SRP. And so you'll go to that.
Who's speaking?
For you.
Hello. Go ahead. Oh, Okay, somebody's speaking about something else. All right. Yeah, I know we're all doing this weird at home thing. No problem, Steven. Okay, so yeah, so right, so we're all working this out as we go along, and I will try to. And I'm kind of I do want to have. I don't want to do like a sort of short answer Canvas exam, or because basically you end up with just some sort of kind of variation of multiple choice, and I think that's sort of not a doesn't really fit this course very well, at least this course very well. So, if I were teaching a different course, I would think about it more seriously. So I want to have something close to what we did on exam one. It'll cover more, but it'll be shorter. So it'll almost be like a little chunk of a final, um, which is good actually. Because the coverage of which should actually be in some ways more less stressful, because when you cover things on a final, um, it's sort of you cover them as a slightly shallower, so it won't in some ways it will not be quite as in depth as our usual exam 2 would have been, but yeah, I'm pretty sure it'll have some variation on you writing on paper and taking pictures of it and submitting it by Canvas. So before I get to Fan's last question, which is a good question, does that make sense? Does that give you some idea what's going to happen with exam 2? Yeah, it'll be very much like submitting your homework. So if I could ask one thing, I know this will be very difficult for those of you who uh, like to write small and faintly. If you could either write a little bigger, and ideally also write in pen. I know people don't like that, but if you write at least a very dark pencil or in pen, that will save my eyesight a little bit. So anyway, we'll see how that happens. And Fan asked a very, very interesting, important question. This might be off topic, but do you know whether the classes will be pass no credit? I would not count on that. So it would make sense to at least give some sort of leeway or a cushion for people, or let me say something that yeah. It would make sense, but I don't get the impression from sort of. I mean, actually, the people I've talked to directly on our campus have some amount of flexibility and seem to express some amount of flexibility in various things. So talk to your advisor. So if you're in trouble, if for example you had to move, if you lost your job in the last few weeks, which I know has happened to a lot of people, if your relatives are sick, if you're sick, or if you just know people are sick, that's also pretty terrible. Um, then I would, if you're in some sort of bad situation because of the pandemic, I would talk to your advisor and see what options that you might have for relieving your stress, so to speak. Does that make sense? Because there will be some options, but will all classes be credit, no credit, or passed? Probably not, because there's definitely I've encountered some flexibility on campus. So anything that we can sort of implement locally, people seem to be more flexible. But for the entire system, for something happening over the entire CSU system, I'm getting the impression of some inflexibility from the big system, which is I I don't want to say something too negative on YouTube, but that's generally, I mean, people have to run a big system, and so it's hard to be flexible when you're running this gigantic machine. It's like turning the ocean liner or whatever. But yeah, I get the impression that system wide there will not be necessarily a whole lot of flexibility. I could be wrong. I mean, we'll all plans are written in sand, and so we'll see. Maybe there'll be more flexibility as the situation continues. Anyway, so I hope that was a little bit reassuring. At least it gives you whatever will happen. Whatever will happen, it won't be so different in many ways from what you were doing before. I'm very aware that life is very stressful right now for everybody, and so stay safe, stay shelter in place, stay home, don't go anywhere for spring break. Take care of yourselves and each other. Take care of your families, And it's really okay, yeah. Than has one last question. Kyle, do you want? Oh yeah. So, will I be available? Yes, I will be available for spring break. For those of you who are my advisees, I apologize for not setting my advising appointments. I will actually. I first sort of had to schedule those around family time, and I think I'll start doing advising appointments over spring break. And so, yes, I will be available for spring break, even if I'm sort of watching my kid for many hours a day. I will still be available to, at the very minimum, to answer your email questions in the evening. So yes, I'll be available. So yeah, so and put things out on the Piazzas. I think our class hasn't used the Piazza website so much, but if you want to try using that, this is actually a good time for that. But like I said, take care of each other. It really has been a pleasure doing this with you. I mean, as a situation considering. So thank you very much for coming by. And those of you who are on YouTube, thank you very much for listening, and take care of yourselves and each other. We're going to get through this, and it'll be okay. All right. So, and I think I better go have lunch with my family. So thank you very much for listening and stopping by, and take care, everybody, and be careful out there.